In this video, we're going to be talking about acid-catalyzed reactions with alkenes. That involves additions and elimination reactions. Now, the first thing to point out is, well, what does this mean? An alkene just refers to a carbon-carbon double bond, and while an acid is just any good source of H+. Now, the simplest way to show an acid is to, over the arrow, have H+. An acid is simply something that gives a proton, something that gives a hydrogen, and what's simpler than just a hydrogen itself? Other good acids that we'll run into in this course most commonly are H2SO4, sulfuric acid, hydronium, which is H3O+, the protonated version of water, any halogen acids, so HBr, HCl, HI, etc., and then a couple other OH acids occasionally, HOCH3, HOET. As far as strong acids go, these are very strong, and these are a little bit weaker, but they can still be used as a proton source. Most commonly, though, for these acid-catalyzed reactions, these are the four I see the most often, and then just H+. Now, how do these reactions work? First and foremost, what you're going to see is that your double bond is going to act like a base. It has electrons, and it's going to use those electrons to go out and grab your proton. And so what you're going to see is the arrow will always start from the center of the double bond and go out and attack that H+. And what you will get is a carbocation on one end of where the double bond used to be, and a hydrogen added to the other carbon. Now, we have to figure out where should that carbocation be placed. It could go on the secondary carbon or the primary. Now, if you remember your rules about carbocation stabilities, the more substituted, or the higher degree, or the carbon with more carbon bonds is where carbocations will feel most stable. And that will always be the place where the carbocation gets added in these kinds of reactions. That means, since it was between a secondary carbon and a primary, the carbocation will be added to the secondary, and that also means that the hydrogen you added in that first step will be added to the primary. Each end of that former double bond gets one thing. Now, a very, very important thing to always be on the lookout for in these questions, these acid-catalyzed questions, because they involve carbocations, are carbocation shifts. The second you make that carbocation, the first thing you should be thinking about, regardless of what was over your arrow, is can that carbocation do a methyl shift, a hydride shift, a ring expansion, move to a more stable position, or make the molecule more stable so the carbocation is a little bit happier. And in this example, that is very much the case. We have a secondary carbocation that is a single bond away from a tertiary carbon. Tertiary positions are much better for carbocation, so that positive charge is very much interested in moving to that position. So what's going to happen is you're going to draw an arrow from the carbon-hydrogen bond on that next door neighbor to the carbocation carbon, and that will show that you've essentially traded places with the two. And so you will get a tertiary carbocation, and that hydrogen over here will now be on this carbon. I'm going to stop drawing the hydrogens right now because they're not so important. We're just following where that carbocation should be. Now, what's going to happen next depends on the question. Something is going to react with that carbocation. And now there are a couple ways that this could go. It depends on what's on the arrow. If you just had H+, well, they would probably never give that to you because you need something more. But let's say they gave you H+ in H2O. Now, the important thing to remember is, again, this H+ could have been any of those acids I listed earlier. Their purpose is simply to get you that carbocation. What's written under the arrow is your solvent, and your solvent is going to be the thing that continues the reaction after you get the carbocation. So, in this case, I have water over the arrow. And what that means is H2O will be over my arrow. Those electrons of this oxygen will be attracted to the positive. And so they will attack. What we're doing is essentially an Sn1 reaction. We made a carbocation, we did our shift, and now a nucleophile is attacking the positive charge. And so what you will get is that H2O added to that tertiary position. Now remember, to do that, the oxygen had to use a set of its lone pairs, which means after this reaction is all done, that oxygen will be positive. And a quick check you can always do is, in this course, general rule of thumb, when you see an oxygen with 3 bonds, it's typically going to be positive. All right, well, we don't leave our answers positive unless the question asks for it, which usually it doesn't, which means we still have one step to go. We need to see that H2O positive neutralized. What's going to happen is another molecule of the solvent, which in this case was H2O, will come in and pull off that proton. So the alkene uses another H2O will use its electrons to grab that proton and kick the electrons onto the oxygen, neutralizing it, giving us the final answer of an OH on that tertiary carbon. Okay? Now, the key points to make of this is, one, you will always do a shift if you have the capability of doing so. The carbocation is unstable, and anything that molecule can do to make itself a little bit more stable is always going to be favorable. These reactions, however, are limited to one shift per question. As we discussed in the shifting video, it takes quite a bit of effort to make a shift happen, and while it's guaranteed to happen the first time, the second time round might take too long, and by that time the water may just come in. So as far as you're concerned, there's only going to be one shift per question. Now let's talk about acid-catalyzed elimination reactions. So an acid-catalyzed elimination will look very similar to the reaction we just did. I'm going to have some source of acid, typically water, but the one difference is in addition to that, you will see the word heat. Heat, high energy, favor elimination reaction. So whenever you see heat and you're stuck between Sn1, E1, Sn2, E2, if you're stuck between that, remember that heat typically hints at the fact you're supposed to be doing an elimination reaction. And what does that mean? In your product, you should be forming a carbon-carbon double bond. Now, most commonly, what you will see on this arrow is not H plus H2O and heat, it'll be H2SO4 H2O and heat, but they're effectively the same thing. Like we mentioned before, H plus could be replaced by a number of different acids. It's just, this is the most common one I see on exams and in the textbook and what we teach, so I may as well be a little more specific. That shouldn't be positive. Now, how does it work? Well, the first step is exactly the same as what we saw before. The double bond will act as a base and pull off a proton from your acid. So one of the hydrogens connected to that sulfur will be pulled off and its electrons will go to the sulfur, and you'll be left with a carbocation. And again, where is that carbocation going to be ending up? Well, I have a secondary carbon and a primary carbon. Secondary is the higher degree, so the carbocation ends up there. The hydrogen will be placed on this carbon on the primary position. Now, in this example, in the previous example, I gave you a tertiary carbon. This example, I gave you a quaternary carbon. Same idea though, you see a secondary carbocation a single bond away from a higher degree. You're going to do a shift. Since this is a quaternary carbon and there are no hydrogens on it, you have to do a methyl shift. So you draw from the methyl bond to the carbocation carbon, and now you have a tertiary carbocation and a methyl where that secondary position was. Okay? Now, how does the elimination reaction work? If this was the Sn1 mechanism like the previous, all that would happen is the water would come in and attack there. However, we're doing elimination because we see heat. What you're going to do is you're going to say, okay, here's my carbocation. That will be one end of where my new double bond will form. The other end must be a single bond away. So we have a couple options. It could be this carbon, or this carbon. Those are all a single bond away from the plus. But now we remember our rule about the formation of double bonds. Double bonds always favor forming where they can be most substituted unless you're using a bulky base. Now, neither the conjugate base of H2SO4 nor water are bulky in any means. Your only bulky bases we teach you about in this course are LDA and terbutoxide. So this is not a bulky base. We want to make the most substituted double bond. So which of these three carbons would give us that? It would be the one here, because if we did that, the double bond would form in the middle, and there would be two carbons coming off of each end. That's as substituted as a double bond can get. So now, how does the mechanism look? Well, in any elimination reaction, you have a base pulling off a proton. That proton will be from the carbon that's a single bond away from your plus charge. So now, who is the base that's pulling this hydrogen off? Is it the H2SO4 minus, or is it the HSO4 minus you made in the first step when you pulled off its proton, or H2O? Honestly, I don't think they really care. I would argue it's probably the water, just because water is the solvent here. There's 1,000 molecules of water to the single HSO4 minus that you made in the first step. Mechanistically, and what they expect you to know on the exam, I don't think they particularly care. Whatever you choose to use, just make sure what happens is that thing that is acting as your base will use its electrons to attack the proton, The proton-carbon bond goes to where the double bond is forming, and that will give you your final product. So you will be left with a double bond straight down the center like that. And here's your product. So this is how acid-catalyzed elimination reactions work. Now, there's one other kind of reaction that we should be paying attention to. And that's where we're not given a solvent, we're just given something over the arrow. So let's say I give you we're just given one acid over the arrow is what I mean. So let's say I give you this 4-membered ring with a double bond like that, and over the arrow you see HCl. Now keep in mind, before I showed you H plus in H2O. This could be HCl in H2O. And if that were the case, you'd protonate the double bond with the HCl, and then the water would get added to that carbocation. But if I leave out the water, well, what are we doing? Well, since there's nothing in the solvent, everything that we're adding is going to be purely from this HCl. So, first step is still exactly the same. The double bond goes out and attacks the proton, kicks out the chlorine, and we're left with a 4-membered ring with an ethyl and a carbocation that got put on the secondary position because it's the higher degree of the 2 carbons of that double bond. Now, again, we have to be on the lookout for shifts, and we see, well, it's a carbocation a single bond away from a tertiary carbon. Your first instinct might be, let's do a hydride shift. However, whenever it's a single bond away from a ring, we know that's actually the hint that we're doing a ring expansion. And ring expansions always get priority over hydride shifts. So how do we do that ring expansion? I see my carbocation, and I see the carbon that's a single bond away from it that's in the ring. I'm going to go one bond further, either this carbon in the bottom right or this carbon in the top left. I only pick one. I'm going to choose the bottom right. And usually in your exam questions, whether you choose one or the other, you'll get the same result, so don't worry too much about which one's the right one to pick. I'm picking this one because I think it's just a little easier to visualize with. So that's the other carbon I'm going to look at. This is the bond that I'm going to do the shift with. So I draw the arrow from that bond to the carbocation. Now how do we draw the product of that shift? What you're going to do is you're going to draw everything exactly the same on the other side of the arrow. In pencil preferably, because then you can erase things more easily. So we said this is the bond that is shifting, which means that is the bond that will get erased in our product. The carbon that isn't already connected to that carbocation will now be connected to the carbon that was with the carbocation. This carbon was positive, but by getting this extra bond here, it will lose that plus charge. However, a new carbon will become positive because we formerly had a bond here, right? This carbon gave up that bond and made a new bond there, so it's fine. But this carbon up here gave up that bond and got nothing in return, so it will now become positive. Now we can just neaten this structure up. It's now a 1, 2, 3, 4, 5-membered ring, so I'm just going to draw a 5-membered ring. On one carbon, there's a methyl. And then counterclockwise to it, a single bond away, is a plus charge. So there's our structure. So we've done our shift, we've got our carbocation, what's going to happen next? Our Cl- is going to come in. If this had been HCl and H2O, everything up until this point would be the same. The difference is if there was H2O there, there's your solvent, and so your solvent would be over the arrow, and that would be what comes in on the carbocation. But since there was no solvent in this example, it's just a matter of the Cl- being there to come in, attack that carbocation, and give you the final product of this. And again, remember, even though this carbocation that we have right here is a single bond away from a tertiary position, we can only do one shift per question. Our shift in this example was the ring expansion. Once that's done, we're done with shifts for the rest of the problem. So even though you think, okay, well, I'd want to do a hydride shift now, it's not going to happen. It's just all the energy that was spent doing the ring shift basically used up your budget for shifting. And that's how you can think of it. As far as you're concerned, any question only involves one shift at most. And so those are the main couple reactions you need to know as far as acid-catalyzed reactions go. H plus with a solvent, doing an Sn1 reaction. H2SO4, H2O in heat, doing an elimination reaction. And then any hydrogen halogen acid, where there's no solvent.